Work done in an adiabatic process. A gas has a well-defined mean energy E bar when its volume is V and mean pressure is P bar. If the volume of the gas is changed quasi-statically, the mean pressure and energy of the gas will then change accordingly. Suppose that the gas is taken very slowly from A to B, as in the figure, while the gas is kept thermally insulated. In this case, P bar is found to depend on the volume as V to minus 5/3. What is the work done on the gas? So it has mean energy E bar, volume V, pressure P bar, and these values will change in the quasi-static process where I have no heat exchange with the environment. It's quasi-static adiabatic process. And I look at the process. The gas is taken very slowly from A to B. So let me see, the gas is taken from A to B. So that is this path here. The gas is following this path. I have the state A here and state B here. And here the pressure is varying with volume as V to minus 5/3. So I noticed that since Q is 0, or rather D bar Q is 0 because it's quasi-static process, it's adiabatic and volume is decreasing, so it's an adiabatic compression. That's the process from A to B, where the pressure is proportional to V to the minus 5/3. So if I write P bar as a constant C times V to the power minus 5/3, and I look at the value of the pressure at point B, so at point B I have pressure equals 32 times 10 to 5 pascals, and the volume equals 10 to 3 centimeter cube, which is 10 to minus 3 meter cube. So I can see that this constant C should be equal to 32 times 10 to 5 pascals divided by 10 to minus 3 to the power minus 5/3. So the 3's will cancel and I will have the minuses canceling, so it becomes 10 to 5. Therefore this is going to become 32 Pascal the unit is not that important, so let's keep it as 32 for now. So the pressure P bar in pascals will be equal to 32 V to the power minus 5/3 in pascals. Okay, and the volume is in meter cube. So this is all in SI units now. Now the work done, D bar W on a gas is minus P bar dV. So the work done from the initial state to the final state minus integral initial to final P bar dV. So this is work done on the gas. So that's something we need to be careful about. It's on the gas, not by the gas. So this is minus integral from initial state to final state, C times V to the minus 5/3. So that will be equal to minus 1 over minus 5/3 plus 1, V to the minus 5/3 plus 1 times C between initial and final volumes. So the work done will be equal to 1 minus 5/3 will give us minus 2/3. Because there's a minus sign, it will become plus. So it's 3/2 volume to the power minus 2/3 times 32 between initial and final states. So this 2 will make this 3216. So it will be 48 V to the power minus 2 over 3 between the volumes. Initial volume is equal to 8 10 to minus 3 meter cube. Final volume is equal to 1 10 to minus 3 meter cube. So I can evaluate this 48 multiplied by the end point 10 to minus 3 to the power minus 2 over 3 minus 8 times 10 to minus 3 to the power minus 2 over 3. So if you calculate this, you find that the total work is 3600 joules. So we have an adiabatic compression process going from point A to B. The volume is decreasing. The gas is kept thermally insulated. That's how I understand it's adiabatic. It's a quasi-static process, and P bar is proportional to V to the minus 5 over 3. So let me just remind you here from your thermodynamics class. In adiabatic process, we have P bar V to gamma a constant, and gamma is the ratio Cp over Cv, molar specific heat at constant pressure and molar specific heat at constant volume. So P bar V to 5 over 3 is a constant here. So gamma is equal to, in that case, 5 over 3. So we will get back to this later on in this course as well. This is from your thermodynamics class. So V bar Q is 0. P bar is proportional to V to minus 5 over 3. What is the proportionality constant? I use one of the points. So let's take point B, where I have 32 10 to 5 pascals as the pressure, newtons per meter square. The volume is 10 to 3 centimeter cube, which is 10 to minus 3 meter cube, which shows me that C should be equal to 32. So it is C times V to minus 5 over 3, and C should be equal to 32. So P bar is 32 V to minus 5 over 3 in pascals. The work done is the integral from initial state to final state of minus P bar dV, work done on the gas. So this is dW on the gas. So if I calculate this integral from initial to final state, the integral of V to minus 5 over 3 is V to minus 2 over 3 divided by minus 2 over 3, but because I have a minus sign up front, it becomes 3 over 2 V to minus 2 over 3. So if I multiplied by C, this 32 here, and if I evaluate it between initial and final volumes, the answer is 3600 joules.